So hello everyone. My name is Mo. Today I'd like to talk about building a verified concurrent file system. File systems are known to be complex and have lots of bugs. A array of file system patches. Okay. Sorry. So file systems are known to be complex and have lots of bugs. A array of file system patches found that about 40% of them are used to fix bugs. About 20% of bugs are concurrency bugs, which are extremely hard to eliminate due to many possible interleavings. And the ultimate goal of building a file system is to build applications on top of it. But the POSIX standard is reported to be vague, especially on concurrent behavior of file systems. For example, it is unclear whether an operation should be atomic with respect to other operations, which makes it difficult to reason about higher level applications. So our approach to these problems is formal verification. We write a specification and prove that the concurrent implementation meets the specification under all possible interleavings. The proof has to be checked by a proof assistant, in our case Quark, to ensure the correctness. It can avoid large classes of bugs, and the specification can serve as a precise interface for applications. There have been many efforts on file system verification. However, this verified file system don't consider multiple concurrency. There are also efforts that provide compositional reasoning for concurrent systems. But fine-grained file systems have very complex concurrence pattern, such that their verification approaches are not directly applicable to achieve our goal of verifying a fine-grained file system. So in this work, we make two contributions. One is a framework called CRLH, or Concurrent Relational Logic with Helpers, for building verified concurrent file system. The key idea is what we call a helper mechanism that allows us to reason about the concurrency pattern of file systems, while still using the underlying Quark framework to mechanically check that all our proofs are correct. On top of CRLH, we also build AtomFS, which is the first verified fine-grained file system. AtomFS uses Python lock for fine-grained synchronization. It is only an in-memory file system, so no quasi safety. But AtomFS can provide atomic interfaces. It is a very clean interface for applications to use because it hides the internal interleavings in AtomFS. Another distinguisher of AtomFS is direct verification in C language. At first, we should define what correct means. So in sequential setting, the file system is correct if the sequential history of invocations and returns is correct with respect to pre- and post conditions of each operation. In concurrent setting, operations will interleave and don't execute in sequence. So how do we describe the correctness of concurrent execution? The idea is, can we still describe the concurrent without the sequential? So we get linearizability, which is a widely accepted correct condition for concurrent objects. It says each method of the object should take effect atomically at some point between invocation and return. This point is called the linearization point. So the concurrent execution can be mapped to a sequential history according to the linearization points. The concurrent file system is correct if for any concurrent execution of the file system, its equivalent sequential history is legal. There are many approaches proposed for proving linearizability. An intuitive one is to build forward simulation between the concrete code and the abstract operation. The concrete code can be seen as a transition system that consists of multiple concrete state transitions, and the abstract operation only has one single transition. The basic idea is to establish the equivalence between them through the simulation. There are three things needed for the simulation proof. First is to define the abstract state and the abstract operation. For example, we may abstract the file system with a traceback. So the abstract make_dir would be specified as an atomic transition on the abstract file tree. Second, we should decide the linearization point. Since it's when effects are published, the abstract operation should also execute at this point to simulate that effect. Also, we need to define the abstract relation that connects the concrete state and abstract state. It also intuitively establishes the correspondence between the concrete code and the abstract operation. It's okay if you don't fully follow here. You just need to remember that previous efforts have proven that once we finish the simulation proof, it further implies linearizability. The idea behind this proof is that for any concurrent execution, we can construct a linearization of abstract operations. The order between these abstract operations is according to the temporal order of linearization points. So let's use the idea to prove a fine-grained file system. Here is the pseudocode of the MakeDR syscall. It's simplified, but it represents the common pattern of path-based operations. After the operation begins, a path name resolution will locate the father directory. Then, in a log-protected correct section, we will insert a new entry in the father directory. Since updates are performed in the correct section, and the effect is accessible to other threads after we release the lock at the end of the correct section, so you can choose the point before unlock as the linearization point, or you can choose other points in the correct section if you will. Similarly, we can decide the linearization points of other path-based operation. If our choice of linearization point is correct and our implementation is indeed linearizable, then we should be able to construct sequential histories for any concurrent execution. But unfortunately, there are cases where our choice of fixed linearization points might fail. Consider this particular interleaving. There are two operations, makeDR and rename, executing on this file tree. Suppose makeDR goes first, traverses to B, and stops before its linearization point. Then rename is able to finish its whole execution and successfully renames A to D. After that, makeDR passes its linearization point and also succeeds in creating a new directory C. This is a perfectly legal interleaving in fine-grained file system. If we try to linearize this interleaving with linearization points, the equivalent sequential history would be that first rename executes and then makeDR. But this is not a legal sequential history, because if rename first modifies the path, the makeDR should fail in the path traversal as the path doesn't exist. We know that the legal history should be first makeDR executes and then rename, but we are unable to obtain such a linearization with the help of fixed linearization points. And we have further checked the other cases to see if they have the same situation. And we found that all failed cases involve rename. So we dig into this case to find the common pattern. We found that rename is a special operation because it can modify an internal inode in the file tree. In some cases, the internal inode that rename modifies might happen to be in the traverse path of another operation. We call this phenomenon path interdependency. At the concrete level, path interdependency is allowed by the fine-grained file system implementation. At the abstract level, our linearization strategy says we linearize at each operation's linearization point, but first executing the abstract rename would break abstract makeDR's path integrity, so it should return failure. It suggests our linearization strategy is insufficient to reason about path interdependency and should be fixed. More specifically, makeDR should be linearized prior to the rename. So our approach is that we adjust the linearization strategy and also linearize when path interdependency happens. Now, when we revisit the previous interleaving, at the rename's linearization point, it should first logically help makeDR commit its fact by executing the abstract makeDR and then commit it itself. The linearization point of makeDR now resides in another operation rename. We call this kind of linearization point an external linearization point. So for a path-based operation in file system, the linearization point is actually non-fixed. It could be in its own code, or it could be an external linearization point triggered by path interdependency. To reason about the external linearization point, we should allow one thread to linearize the abstract operations of other threads. Such a mechanism is called helping. Prior work has introduced a shared thread pool in the abstract model to formalize helping. The shared thread pool matches each thread to the state of the abstract operation, which could be either that the abstract operation needs to be executed with some arguments, or the abstract operation has finished with some return value. So one thread can perform helping to another thread by updating its abstract operation state to indicate that it has been executed and therefore linearized. But in file system, helping is implicit. There's no global information about which threads to help. Also, a rename may help many threads and should carefully decide the helping order. And there is a most challenging case, which we call recursive path interdependency. There may be multiple renames chaining together, each rename modifying another rename's traverse path. So in this case, although rename 1 and rename 3 are operating on different paths, but rename 1 may need to help rename 3 because they are recursively related through rename 2. I will take the first challenge as an example to explain our idea. We extended the previous helping mechanism with some file system-specific notions to handle these challenges and name the new mechanism as helpers. First, we propose a helper metadata, which extends the short thread pool with other necessary fields. Users can instantiate the helper metadata, for example, by adding a log path in the descriptor to record the path that the current thread has traversed through. The purpose of these extensions is to help decide whether an operation should be linearized before another operation. For example, when the rename is about to pass its linearization point, it can use the log path information to compute which thread's log path contains its own log path. So this thread should be linearized before rename and should be helped. And this linearized before relation should also include recursive dependencies if there are. So in summary, helpers allows us to reason about the external linearization points in file system. With the series ready, we implement the CRH framework in Quark, and the interface of the framework is the following judgment. The precondition code and postcondition are similar to that of Hall logic in sequential reasoning. To reason about fine-grained concurrency, CRH adopts an approach called the LRG, or local relay guarantee. Here, I will not go into details about LRG. And the feature of CRH is relational reasoning. Namely, all assertions not only describe the concrete state, but also include the abstract state to establish correspondence between the concrete code and abstract operation. To specify a particular operation, say rename, we instantiated the abstract operation in the precondition to the abstract rename as a specification. CRH provides inference rules to assist proving that the implementation meets the specification. We have system rules to reason about C program and helping rules to perform helping. We also have a correctness theorem to ensure that the logic indeed establishes linearizability. Note that we have modeled C language in Quark, so we can directly verify the file system implemented in C and run them as ordinary file systems. On top of CRH, we build and verify AtomFS. The most difficult part of proving AtomFS is to find and specify all the invariants on the short states, which are necessary for the simulation proof. Here, I will introduce a most important and interesting invariant, which we call the non-bypassable invariant. It is because we found that operation bypassing will lead to non-linearizable behavior. So operation bypass means if an operation 2 doesn't always hold a lock during path traversals, another operation 1 can bypass it and access its descendant inodes. When combining operation bypassing with path interdependency, we can easily construct non-linearizable behavior. So in this execution, rename will first modify the operation 2's traverse path, so it should be linearized before rename. And then an operation 1 happens after the rename finishes, so it should be linearized after rename. But if operation 1 can bypass operation 2 and modify the state operation 2 will use in computing the return value, then in the sequential history, the return value could be illegal because the operation 1's effect happens later. So we successfully construct a non-linearizable interleaving. You can read our paper for a concrete case. In AtomFS, we use lock coupling for path traversals. We will first acquire the next anode's lock before releasing the current, so it can forbid bypassing by always holding a lock. And we'll get a non-bypassable invariant to formally capture this property. We noted that it will reduce the parallelism of our file system, but we can provide linearizable interfaces. So you can see it's a trade-off between performance and reasoning. Here, we sacrifice performance to make AtomFS easier to reason about. We implement CRH and AtomFS in Quark. The whole work took several researchers 1.5 years. The CRH framework is about 100,000 lines of code, and we write about 6,000 lines of proof for AtomFS. We run AtomFS as a user-level file system. Evaluation shows that our single-core performance is better than DFSQ, a high-performance verified file system, but slower than ext4 and TempFS. Our multi-core evaluation shows even better scalability than ext4. The main reason of that is AtomFS does not bypass VFS-level path lookups, and that code is scalable. Also, we can see that as costs increase, the low coupling traverse becomes a major bottleneck. And the throughput of AtomFS is about 6 times lower than ext4 because we didn't implement many optimizations used in ext4. To conclude this talk, we observe that the path interdependence phenomenon will lead to the external linearization important challenge, and we propose a helper mechanism to handle such challenges. We built a framework called CRH and successfully applied CRH to verify AtomFS, the first verified fine-grained file system. You can find more information at the following URL. So thanks for listening, and I'm ready to take questions.
Any questions? So I have one question. So the previous paper talks about verifying both concurrent and crash-safe systems. So here it looks like you guys spend a lot of effort verifying concurrent file systems. So what would be the additional effort needed to verify crash safety on top of what you've already done?
Yeah, so that's a good question. So the question is about how do we plan to support crash safety? I think first of all, you should have a practice condition. For example, you can use the concurrent recovery refinement in Perennial. And then you should decide what properties you want to prove. If you still want to prove an property like crash automaticity, then you would still need helping because phenomena like path interdependence would still exist in the crash setting. So, indeed, there is work to do. So we leave this as our future work.
Okay. I have another question. So it looks like rename is the culprit here that complicates your verification. What about just changing the file system implementation of rename so that rename becomes a lot easier in terms of verification? Have you thought about that?
Yeah, so this is also a good question. Yes, we can see that all the problems comes from rename. So we have thought about changing the semantics of rename, but in this work we choose to follow the POSIX standard, and our future work will think about this.
Let's thank the speaker.